Hi everyone, my name is Huang Qiang. I'm a research fellow at the National University of Singapore. Today I will present our work entitled Point to Hyperplane Nearest Neighbor Search Beyond the Unique Hypersphere. It is a joint work with Dr. Lei Fan and Dr. Anthony Tang. Our source code is available from this link. We first formalize this problem. Given a database of n data objects and a hyperplane query queue, the point to hyperplane nearest neighbor search aims to find the data point P star, which is closest to the hyperplane query queue. For example, consider the figure on the right. There are three data points P1, P2, and P3 on a 2D plane. And there exists a blue line, which can be considered as a hyperplane query. As you can see, P1 is the closest data point to the hyperplane query. So P1 is the data object P star we aim to find for the point to hyperplane nearest neighbor search. Given a data point P and a hyperplane query Q, the point to hyperplane distance is defined as follows. As you can see, the numerator contains an inner product operation and an absolute value operator. This problem is more difficult than the classic point-to-point nearest neighbor search, based on two aspects. First, the data points and the query are not in the same dimension. Second, since the point to hyperplane distance contains the inner product operation and the absolute value operator, it will violate the triangle inequality, and then so it is not a metric. Therefore, many state-of-the-art methods based on the distance metric property may be not suitable for this problem. This problem has wide application in many machine learning and data mining tasks. For example, in the larger scale IT learning with SVM, its goal is to iteratively generate the decision boundary or the hyperplane query we call here, and then they will ask the annotator to label the most uncertain data in a massive unlabeled pool. The selection criteria for the most uncertain data is to use the point to hyperplane NN search to find the data objects which is nearest to the decision boundary. For example, the blue color we show here. The data point with the blue color we show here. So if we could design efficient method for point to hyperplane NN search, we can speed up the learning period for the larger scale IT learning. This problem also have other applications such as maximum margin clustering, and large margin dimensionality reduction. In the literature, there exist many hyperplane hashing schemes for this challenging problem, such as EH, which is published in NeuroRisk 2010, BH, which is published in ICML 2012, and MH and DSH, which also published in CPR 2016 and POST 2018, respectively. Their basic idea is to assume all the data points are on the unique hypersphere. For example, the L2 norm of all data points are normalized to 1, and then the point to hyperplane distance can be transformed into the angular distance. So they could design different locality sensitive hashing function to achieve sublinear time for this challenging problem. However, the unique hypersphere assumption is a very strong assumption. In many applications, such as dimensionality reduction and clustering, this assumption may be not satisfied. However, if we doubt this assumption, this method may be arbitrarily bad for this problem. What was worse, if the point to hyperplane distance is close to 0, they will require about big O(n) number of hash table and nearly linear query time. To the best of our knowledge, there is no sublinear time method for point to hyperplane NN search beyond the unique hypersphere. On the other hand, for the problem of maximum inner product search, a symmetric transformation is a key to remove the unique hypersphere assumption. Similar to the point to hyperplane distance, the inner product is also not a metric, but this problem can be well sorted by the asymmetric LSH in sublinear time. Their basic idea is to design different asymmetric transformation P and Q for the data objects O and Q respectively. So they could convert this difficult maximum inner product search problem into the classic point-to-point NN search problem. And then they could leverage many efficient sublinear time methods for point-to-point NN search to deal with this challenging maximum inner product search problem. However, compared with the inner product, the point to hyperplane distance contain an absolute value operator. So existing asymmetric transformation for maximum inner product search cannot be directly used for the point to hyperplane NN search. So an interesting question is that, can we design a new asymmetric transformation for the point to hyperplane NN search problem? Before we answer this question, since the formula of point to hyperplane distance is a bit complicated, so we first simplify this distance. We propose two operations in the preprocessing phase before the point to hyperplane NN search. First, we extend all the data point P by one dimension with 1. For example, we will construct a new data object O, which is a concatenation of the original data point P with a scale value 1, so that all the data objects O and the query Q are in the same dimension. Second, we assume the denominator of the point to hyperplane distance is equal to 1. Otherwise, we could rescale the query Q to satisfy this assumption. It is reasonable because for the non-trivial query Q, distance is fixed and is not equal to 0. So we could always divide this part to satisfy this assumption. After these two operations, the complicated formula of the point to hyperplane distance can be simplified as the absolute inner product between the data objects O and the query Q. And then the point to hyperplane distance can be also considered as a point-to-point minimum absolute inner product search problem. Here are the formula. So after the distance simplification, we propose a two-step asymmetric transformation for point to hyperplane NN search. In step 1, we propose two object embedding function f and g for the data point O and the query Q respectively. Here are the formula. After this step, we can see that the inner product between O point and Q point is equal to the square of the absolute inner product between O and Q. So with this step, we can remove the impact of the absolute value operator. In the step 2, we propose two hypersphere transformation P and Q for the data point O point and the query Q point. Here are the formula. After this step, we can see that the L2 norm of the PO point is equal to the L2 norm of the QQ point and is equal to a fixed constant. So with this step, we can remove the unique hypersphere assumption because all the L2 norm of the data point PO point for now are equal to each other. So with the two-step asymmetric transformation, we can convert the challenging point to hyperplane NN search problem into the classic point-to-point nearest neighbor search problem. Here are the induction details. However, our object embedding function P and G will increase the data dimension from D to big O D square. So it will increase the query time complexity. To elevate this problem, we propose to approximate the object embedding function f and g with randomized sampling, so that the data dimension can be reduced from the big O D square to an acceptable value. We formally demonstrate this with lemma 3.1. However, due to the time limit, we omit the detail here. So with two-step asymmetry transformation, we propose the first provable method called nearest hyperplane hashing, or simply called NH, for the point to hyperplane nearest neighbor search beyond the unique hypersphere. We define an NH hash family of hash function Hn as follows. It can, as you can see, the hash function Hn can be considered as a hyperfunction of the random projection LSH function HAB and the two-step asymmetry transformation. A basic finding in this paper is that we formally demonstrate that the NH hash family of the hash function Hn is locality sensitive to the point to hyperplane distance. The NH scheme is quite straightforward. It can be considered as the NH hash family combined with a state-of-the-art point-to-point nearest neighbor search scheme called LCCS LSH, which we published in Sycamore 2020. We further analyze the property of NH, and we formally demonstrate that NH enjoy quality guarantee for the point-to-hyperplane NN search. It has sublinear query time and subquadratic space for this challenging problem. However, similar to the existing work like EH, BH, and MH, if the point to hyperplane NN search is close to 0, the NH may require linear query time. To fix this problem, we develop another hypersphere transformation Q point for the Q point we show here. So we can also convert the point to hyperplane NN search problem into another classic point to point furthest neighbor search problem. And then we propose FH for point to hyperplane NN search. In NH, we similar to the NH, we also design an FH hash family and show that it is locality sensitive to the point to hyperplane distance. NH is also quite straightforward. You can simply consider it as the FH hash family combined with a state-of-the-art furthest neighbor search method called reverse course, which we published in TKD 2017. We also analyze the property of FH and show that it also similar to the NH. We also show that it enjoy quality guarantee for point to hyperplane NN search, even though its time complexity is worse than NH, but it has better practical performance based on our experimental result. So in the experiment part, we will study the performance of NH and FH over 5 real-life datasets across different domains. And then for each dataset, we will generate 1,000 hyperplane query for evaluation. Here we consider 2 cases, unnormalized cases and the normalized cases. Here we would like to claim that all the dataset we select are unnormalized. Here we consider the normalized cases because many state-of-the-art methods, they are good at these normalized cases. So we aim to make a comparison with them in a fair setting. And then we will select 4 competitors, two from including 2 state-of-the-art methods, BH and MH, and 2 trivial baseline we call random scan and sorted scan. For the sorted scan, we will first sort all the data points based on their L2 norm in ascending order, and then we will scan the data point from the lowest L2 norm to the highest L2 norm. To study the query performance, we consider the recall fraction and running time to study the accuracy and efficiency trade-off. We also consider the index size and indexing time to study the indexing performance. In the first In the first experiment, we first study the query performance. Here we show the query time record curve and the fetch-run record curve in this figure. Here the red, blue, and green line are the method we propose, and the rest 4 lines are the competitor. As you can see, the method we propose, especially FH, is around about at least 3 to maybe 100 times faster than the best competitor, except the dataset M shown. In the dataset M shown, the performance of shortest scan is comparable to FH. However, the performance of shortest scan is not very stable. For example, in the dataset Yap, Music, and Glock, the performance of shortest scan is the best among all the methods we show here. So we could claim that FH and NH we propose is more efficient and has better trade-off between accuracy and efficiency than other competitors. In the second experiment, we study the indexing performance. We plot the query time index size curve and the query time indexing time curve here. As you can see, the data point from FH is closer than the data point from other methods. So we can see that the method we propose, for example, FH and NH has better trade-off between the query time and indexing performance. Finally, in the third experiment, we also show the result on normalized data. However, as you can see, even on the normalized data, the performance of FH and NH still better than BH and MH. For example, for the curve for the FH and NH is lower than the curve of BH and MH. So we can claim that the method FH and FH we propose outperform the two state-of-the-art method BH and MH. Finally, we make a conclusion for our paper. We investigate a fundamental yet very challenging problem of point-to-hyperplane NN search beyond the unique hypersphere. And then we introduce a novel two-step asymmetric transformation to convert the point-to-hyperplane nearest neighbor search problem to the classic NN search or FN search problem. And then we develop two hyperplane hashing scheme NH and FH and do some theoretical analysis for them. Finally, we use extensive experiment over 5 real-life datasets to demonstrate the superior performance of NH and FH. I think that's all for my presentation. Thank you for your attention.